Welcome to another episode of chemistry. Today we're going to be doing more drawings with double bonds. We'll also get some triple bonds in, and then lastly we'll talk about these things called polyatomic ions and how we draw them. You'll notice that for these three problems I kind of got a head start on them. What I want you guys to do is take a moment, go ahead and make these Lewis dot structure drawings, and while you're doing that I'm just going to finish dotting everything up. So pause the video, take a moment, and do these structures please. Okay, looks like I'm ready to go on the first one. If you need more time, pause the video. Here's what I'm thinking. Each sulfur has 6, and carbon's got 4 over here in the middle. So what I'm going to do here is put a dot here and draw a line here. That's going to give carbon 6 now. 1, 2, 3, 4, 5, 6. And sulfur's going to have 2, 4, 6, and 8. Carbon over here, we'll draw a bond here. This is going to look kind of messy. And we'll draw a bond here. So carbon has 2 double bonds, and so then each sulfur has 1 double bond, 2, 4, 6, 8, 2, 4, 6, 8. So we're good there. This is what the final structure should look like, a lot nicer. Hydrogen each has 1 electron, and nitrogen's got 5. Look at how strategic I'm drawing everything. This one should have been pretty easy. It's just single bonds. And boom, we've got HNO3. NH3. Oxygen's a little bit trickier. Well, bam. Here's what it should more or less look like. Here we go. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Great. So here's what I'm going to do. I'm going to draw a single bond over here and a single bond over here. Now what you'll notice is this oxygen in the middle has 8. 1, 2, 3, 4, 5, 6, 7, and 8. This oxygen has 7, and this oxygen has 7. So if I form another bond here, that's going to be trouble. And if I form another bond here, that's going to be trouble because then my central oxygen has 9, even though my outside oxygens have 8s. So actually what I'm going to do is I'm going to very quickly remove this electron over here and also this one and just kind of rewrite them a little bit. So I moved 1 electron from here and 1 electron from over here. Draw that bond. So now this oxygen has 8. I didn't change the number of total electrons. I just moved this guy from here to here and this guy from here to here. 1, 2, 3, 4, 5, 6, 7, 8 for that oxygen. And then 9 for this middle one, and 7 for this outside one. So what I'm going to do then is I'm actually just going to move, if I can click on it, I'm just going to move this electron from here over to here, and that's going to give me 8 over here, and then it's going to give me 8 over here as well. 2, 4, 6, 8, 2, 4, 6, 8. So they've all got 8. This is the final structure. What you'll notice here is that O3 is the same as SO2, which if you remember, that was kind of the difficult problem we worked on at the end of the day yesterday for notes. So you saw this structure before. You know how to draw this. It just was disguised a little bit. So one of the first things I want to talk about from yesterday is something that hopefully will help you. This was a huge eye-opener for me when I was learning Lewis dot structures. If we look at the periodic table for a second, and these are our 3 compounds that we just drew, what you'll notice is things in the same row have the same number of valence electrons. So carbon and silicon both have 4 valence electrons. Oxygen, sulfur, and selenium all have 6 valence electrons. And remember, the goal is to get to 8 or 2 in hydrogen's case to be nice and stable. Now, what that means then is that, let me just kind of zoom in on these nonmetals that bond and zoom in on hydrogen on the next slide here. So there they are, nonmetals that bond. Here's what this means. If carbon and silicon both have 4 valence electrons, their Lewis dot structures are both going to be the same, which means they'll bond the same way, they'll form the exact same structures. The only thing that's changing here is their actual letters, C versus Si. So if we had CS2, it would look exactly the same as SiS2. The same thing is true for nitrogen. Whether we have nitrogen or phosphorus, they're both going to have 5 valence electrons. So their structure is going to look exactly the same. It's just going to be N instead of P. So NH3 would be the same as PH3. Same thing is true for oxygen. Oxygen, sulfur, and selenium. They all have 6 valence electrons. So again, they're going to look the same. It's just the dots will be the same. It's just the letters inside will be different. So instead of looking with CS2, that would be the same as CO2. We did CO2 yesterday. So, and then of course the same thing is true for the halogens over here, right? Hydrogen has 1 dot, which is kind of similar to fluorine, chlorine, bromine, iodine, and acetine, which all have 7 dots, right? Either way, they all form 1 bond. So it's going to look the same for all the halogens, except the letters will be different. And halogens will look the same as hydrogen, except you won't have those dots on the outside. So when I learned this, this really opened up a lot of my eyes. That's not correct math or English. It really opened my eyes up because look, if we have CS2, that's one structure, but it's using 1 carbon and 1 from the oxygen, sulfur, selenium. So there's about, 5 other different formulas I can ask, and they all have the same structure. So 6 different formulas, they all have the same LDS, Lewis dot structure. That was eye-opening for me. The same thing is true for O3. I have 3 of these guys that are all in this column. So there's a bunch of different ways I could ask the same question, and I get the same formula every single time. If it's my job to make like 50 of these practice problems, you better believe that I'm double dipping on some of these structures. And that sometimes I'll give you the same answer just with a different formula, with a different setup. So if you can notice that, that's going to save you a huge amount of time. NH3, it turns out there's 12 different formulas I could have here. Because look, I could change H with any one of the other red halogens, and I could change N with P. So that gives me all these different structures and all these different formulas, and look at the structures. They all look exactly the same. So I think that's something that's helpful to know here, folks, is that a lot of these structures are going to be very similar. It's just the letters are going to look different, but it's the same answer. Okay, hopefully that opened up your eyes for you. Hopefully that was like a little aha moment. If not, I'm sorry. Let's move on. Okay, we're going to talk now about something called polyatomic ions. Polyatomic ions, remember, are a group of atoms and they have a charge. So here's what that meant back in the day. A negative charge meant add electrons. So in the case of NO2, we have 5 electrons from N, we have 6 electrons from each O, and this negative charge means add 1 extra electron. So when we draw it, we're going to draw out N, we're going to draw out our 2 O's, we're going to connect them, and then we get to kind of add in this extra valence electron wherever and whenever we want. So if we're looking at this structure right now, we'll see that they all have 7, which is kind of nice. That's a good spot to be at, right? Let's go ahead and let's go ahead and add our extra electron right over here. Why not? We could also form a double bond. That's what we're going to have to do next. So now you'll notice that this oxygen has 8 valence electrons. 7 and 7 over here, we're going to have to form a double bond, so that becomes 8 and 8. So I'm going to move this electron over here, this electron over here. Oh, come on, that's pretty cool. And then we'll form a bond there, and when we do that, notice how they both change to 8, because now we've got 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Now, you added an electron. You don't have to change the color of the electron, but there is a way we want to signify that, hey, an electron was added in this structure. Otherwise, it would just be NO2, which is totally different. Nitrites versus nitrous gas. Totally different structures, have totally different properties. So what we do as chemists is we put brackets around the whole structure, and then we put the charge at the end. So in this case, the charge was a negative or a -1. So I'm just going to write a little -1 over there. In case you couldn't guess, positive charges mean you remove electrons. Remember, electrons are negative, so if you have a positive charge, that means you have 1 fewer electron. So what this is going to mean here is it's going to mean, we're going to have to get rid of 1 electron in this case. So why don't you go ahead and take a moment and try out H3O. Hopefully you took your time. Here we go. All right, here's oxygen. Here's my three H's. And what you'll notice is I can really only form bonds between these two before we run into a problem. Here's the problem. Hydrogen's got 2, so it's stable. Other hydrogen's got 2. Oxygen's got 8, so it's stable, but I haven't connected this one hydrogen yet. So I would kind of follow this program where draw the dots and then connect as much as you can before you run into a problem. Now, the solution to the problem is the same as it was in the previous problem. In the previous problem, we needed to add 1 electron. In this problem, we're going to need to remove 1 valence electron. And that really helps us out. Because if we remove this valence electron over here from oxygen, I'm just going to turn that purple. Let's get rid of it. Now, instead of having 8, oxygen's really just got 7. And then we can move it over. We can form a bond. And now, instead of having 1, we have 2. Instead of having 7, we're back at 8. Don't forget to include those parentheses. Don't include a +1 charge. So, 3 things I would write down. Negative charge means add electrons. Positive charge means remove electrons. And you always have to add brackets and a charge to the polyatomic ion. I can't tell you the number of half a points I've had to take off because people forget the brackets or they forget to put the charge with the brackets. So make sure you do both of those things. Okay, here are a couple practice problems. Go ahead and take your time to practice them. Meanwhile, I'm going to write these down. I didn't get a chance to animate these guys. 2, 3, 4, 5. Yeah. And then 1, 2, 3, 4. Okay. Here we're going to take a stab at Cn. C's got 4. N's got 5. And then this -1 means we're going to get to add 1 extra electron. +1 E minus. I'll throw that in there. Okay, so form a single bond. Well, bam. Now we have 1, 2, 3, 4, 5. And nitrogen has 1, 2, 3, 4, 5, 6. Let's go ahead and make another bond. Now nitrogen's got 7 and carbon's got 6. A third bond, and nitrogen has 8 and carbon's got 7. So this is pretty much all we can do. If we form a fourth bond, first off, we don't have quadruple bonds. But second off, and more importantly, then nitrogen has more than 8. Now it's got 9. So remember, we've got that extra electron to add. We're just going to add it right here. And that, in fact, is our final answer for the first one. For the second one, NH2, here it is. Here's N, 1, 2, 3, 4, 5. Here's my H, and here's my H over here. Put a dot next to each one of them. Connect everything up. Both my H's have 2, but my nitrogen's got 2, 4, 6, 7. So to make that even, we're just going to put a little dot over here. Perfect. Those are 2 answers to the polyatomic ion questions, except for one thing. I forgot to include brackets. So you'll notice that my final answers over here, I showed you kind of where I would have put the extra electron. You kind of have to put one next to carbon and nitrogen. It doesn't necessarily matter where though. You could have put it on the top, on the bottom, whatever. But make sure you include those brackets and you include that negative charge in each one of those cases. Great. Couple more. Oh yeah, that's just kind of what we've said already. Make sure to add brackets and a charge to your polyatomic ion. And remember, positive means you remove electrons, negative means you add electrons. Okay, we're going to skip these. That's the answer right there. And I wanted to end with this guy right here. You'll notice it's SO3 2- versus just regular SO3. So in this one, you're going to have 2 extra electrons. Go ahead and take a moment to try these practice problems out, please. Okay, we're going to have 18 from our 3 oxygens. We're going to have 6 from our other sulfur. So let's draw this out. Okay. You can fast forward through this. I know this has got to be super boring while you do this, or you can just use this time to make sure you actually draw the structure. Either way. Okay, and last one over here. 1, 2, 3, 4, 5, 6. Let's bond everything with a single bond. Okay, now, since we're forming a single bond with something that has 6, that means all of our oxygens, since they all have 6, single bond, they all have 7. So 1, 2, 3, 4, 5, 6, 7. And that's true for all of them. Sulfur, however, because it has 6 and we're forming 3 bonds to it, it's going to have 1, 2, 3, 4, 5, 6, 7, 8. It's going to have 9. So the nice thing is we get to add 2 electrons. So I can add an electron to this oxygen over here, and I can add an electron to this oxygen over here. That gets them both to 8, but unfortunately this sulfur is still at 9, and this oxygen is still at 7. So what we're going to have to do is we're going to have to actually take this electron and move it over to this oxygen, so that sulfur loses 1 from 9 to 8, oxygen gains 1 from 7 to 8. So I'm going to go ahead and do that right now. Erase this guy, and we're going to add in, oops, oh my gosh, this is like the worst part. Add in this guy right over here. And so our final answer is going to look like this. 3 single bonds coming out of sulfur and 6 dots surrounding each oxygen with 2 dots on sulfur. So that was because I had to add 2 extra electrons. If I don't add 2 extra electrons, I have kind of a very similar issue, but I'm going to end up with a different answer. So let me just give me a second to draw it. Go ahead and make sure you're doing this as well, that you're following along. Okay, so we form our single bond here, we form our single bond here, and right away we are at 8 valence electrons for these 3, or sorry, we're at 8, 7, and 7. Now, if we form a bond here, we're in trouble because that's going to give sulfur 9. So we're actually not going to form a single bond here. Instead, what we're going to do, this is pretty complicated, right? Is sulfur has too many electrons. If we form a single bond here, it's not going to be enough. We don't have any extra electrons to play with. So what we're actually going to do is we're going to move some electrons off of sulfur onto the oxygens. So I'm going to take 1 electron, move it over here, 1 electron, move it over here. Let's go ahead and do that. Erase it, erase these 2. And then when I do that, I'm going to put them over here. So I didn't add or remove any electrons, I just moved 1 over here and 1 over here. Oxygen's got 8, oxygen's got 8, sulfur has 6, this oxygen has 6. Well, that's really, really nice, because now if I form a bond here, they both have 7. If I form a, sorry, let me move this. Just going to move this dot over here. Oops. And if I move this dot over here, now when I form a second bond, currently 2, 4, 6, 7, 2, 4, 6, 7. So if I form a bond here, now they both have 8. What I want you to notice here is by creating a double bond, instead of 3 single bonds, I reduce the total number of electrons from, in this case, let's see, it's 26, because I've got 6 plus 18 plus 2, 26, versus over here, I have 2 fewer, I've got 24. So what this means is sometimes you won't always know exactly the right situation to go with, but if you notice that you have too many electrons, what you can oftentimes do is you can eliminate 2 pairs, like this pair here and this pair here, and replace that with another bond, and that will keep each electron as having 8, right? In both these cases, sulfur's got 8, oxygen's got 8. So it'll keep the total number of valence electrons, it'll change it by -2, it'll decrease the total number of electrons, but each atom will still have the same number of electrons. They'll still act like they have 8. So that's a helpful hint. Hopefully that made sense. And hopefully you guys have a great day. That's about all we're going to talk about today. There'll be plenty of practice with this just so you guys can kind of get better. Let me know if you have any questions. Take care of yourselves. We'll see you next time.